what we have learned so far? We learned that the Laplace of 1 is equal to 1 over s, or the inverse Laplace of 1 over s is equal to just 1. 1 over s is a function of s, so you can write it as f of s. We learned that the Laplace of t is equal to, well, 1 over s squared, another function of s. For inverse Laplace of 1 over s squared is equal to t, and the rest of those Laplace transformations and their inverses. Now I expect you to ask, what if I want to find the Laplace of the derivative of a function? If we assume that f prime is continuous when t is larger than equal to 0, using the definition of Laplace, it is equal to the integral 0 to infinity e to power negative st f prime of t dt. By using integration by parts, we can write it this way. We're going to have e to power negative st f of t ranges between 0 to infinity, plus s, the integral 0 to infinity e to power negative st f of t dt, which is nothing but, here you have negative f of 0 plus s, and this is just the Laplace of function f of t, which is going to be a function of s. So this guy becomes negative f of 0 plus s times f of s. So it means that we can write down the Laplace of the derivative of function f as s f of s minus f of 0. So if we have an initial value problem, we can plug in f of 0, whatever the value is, and then use the Laplace of f prime as s of fs minus that value. Now I expect you to ask, how do I find the Laplace of the second derivative of the function? The same process by using the definition. The Laplace of the second derivative of the function is equal to, by definition, 0 to infinity e to power negative st f double prime of t dt. Again, by using integration by parts, you get e to power negative st f prime of t ranges between 0 to infinity, plus s, integral 0 to infinity e to power negative st f prime of t dt. This is equal to negative f prime of 0 plus s, and by definition, this is the Laplace of f prime of t. But we know that we define f prime of t, which is s f of s minus f of 0, so this guy becomes negative f prime of 0 plus s f of s minus f of 0. If we distribute s into parentheses, the Laplace of the second derivative of f is equal to, well, here you have s squared f of s minus s f of 0 minus f prime of 0. Well, by the same logic following the definition, the Laplace of the third derivative of f becomes s cubed f of s minus s squared f of 0 minus s f prime of 0 minus the second derivative of f at 0. So whenever we're solving a differential equation and you're dealing with the first derivative or second derivative or third derivative using the Laplace transformation, we can always use these substitutions.